All right, now I promise you that I am going to make this day 4 and day 5 one go fast, and we can get her done for the rest of this particular unit. So day 4, main topic that we're going to be discussed here is what's referred to as an inscribed angle. Now, we've never seen an inscribed angle before, but the concept of it is really pretty simple. Now, what I'm going to basically do is I'm going to add a little bit to this picture. So the idea is that the inscribed angle is where they're showing it right here. But I'm going to go back to what we've known in the past just for a second, and I'm going to put the center inside here. Now, we've actually drawn angles that came from the center, and they would go out here to this particular point A, and they came out here to this point C, all right? And that was referred to as a central angle. Now, this is just good reminder stuff that's going on from day 1 and day 2. And there was something to be said about the central angle and what it did. The central angle and the arc that it ate, the intercepted arc that it ate, these two concepts were exactly the same size. So if I said that this was a 60-degree angle, that'd be a 60-degree intercepted arc. So the central angle equaled the arc it ate. Okay, or the intercepted arc. Now, here's the question, and this is what I'm really posing to you. If I took the center of this angle and I pulled it, and I was like stretching, and then I stick it instead of to the center of the deal, it sticks to the side of the circle. It's no longer going to be a central angle. It's going to be an inscribed angle. Now, an inscribed angle, so we can kind of get a definition here, has its vertex on the circle. And I'm going to put that in very important words here, on the circle. Now, if I do that and I stretch this angle out, you can probably tell that the angle's going to get smaller and smaller, so it's not going to be a direct equal concept of what's going on there. There's no way that those two things are going to be the exact same size. Now, the intercepted arc didn't change its size. It's still, let's say, 60 degrees, but the inscribed angle got pulled further down here into the corner, and now it's a different size than the intercepted arc. It's not the same like that guy was. Inscribed angles and their measures are that the inscribed angle is equal to 1/2 of the arc. It's not going to end up being exactly the same. It's a 1/2 concept. So if this guy was, say, 60, then the inscribed angle over there would be a 30-degree angle. The inscribed angle is always smaller than the arc. It's always half of whatever the arc size is. Now, this only happens if the angle is on the circle. So you got to make sure that it's described that way. Now, if they give you the angle and you want to go backwards to the arc, there's this concept of either is it half or is it double. Remember that the inscribed angle is the smaller part, so you're going to want to times this by 2 to get out here to the intercepted angle. So 23 times 2, we'd end up with a 46-degree angle. All right? Pretty straightforward. It's nothing really hard. Now, if you've got the arc already and you've got to go backwards to the angle, you're going to divide this answer by 2, and 162 divided by 2 would end up giving you like 81 degrees. Okay? So 81 degrees for that particular deal. Now, you're probably going to notice that these angles right here, they really can't get overly big. The biggest they could possibly ever get would be maybe 180 degrees. So keep in mind, they can't get too big. Now, if they want you to find something that's not directly related, they've got an arc over here that they don't have the answer for. Now we just got to rely on some of our background information, like that circles add up to 360. And if I take that 120 away and I take that 140 away, I would end up with, let's see here, a little subtraction. 6 minus 3 minus 4, that's 0. And then 3 minus, that's 100 degrees. Now that is 100, but that arc over there is not going to be 100. He's going to be half the size of the arc he eats, or 50 degrees. Okay, this is really not that bad. And I found that if you trace the actual lines back too as well, if the picture starts to get confusing, trace them back with your fingers so you know about which inscribed angle they're specifically talking about, okay? Now, here's a great example of that, tracing it back. This 27-degree angle is supposed to be for this corner right here. So if I trace this out with my fingers, I'd be like, oh, it's hitting right here at B. And if I trace this guy out like this, oh, you're like, oh, it's hitting right here at C. This must be the intercepted arc, and that would be twice the size of 27, which would be 54 degrees, okay? So make sure that you're tracing things out. Now, number 5 does a really good job of making sure we understand the whole concept as a whole. First off, this BOC angle that's right here, that's a central angle. And here's the deal about central ones. Central angles are equal to the arc. So if I look at that guy being 132, that would mean that this intercepted arc right here has got to be 132 as well. Okay, well, wow, that's great, but that's not the angle we're looking for. We're looking for this guy back here in the back of BAC. Back, get it? Funny. But that's an inscribed angle, and so this 132-degree angle has to be cut in half to come back there. And 132 cut in half is going to be equal to 66 degrees? I think that's right. All right, 660, yeah, I think I'm on the right path. All right, got the idea? Central versus inscribed angles. Now, what are we going to do with that information here in the next concept? Now, this next concept is called the two inscribed angles theorem. So think about what it's saying. It's saying that you got two inscribed angles, and it basically boils down to that if you've got this one inscribed angle here at 3x, and I'm just going to kind of go, oh, it's all the way out here, and this one's going all the way out here, and it's eating this arc right here. Okay, so you're like, okay, that would have to be double the size of that angle, but I don't know what that is. Here's the concept. Look at this one over here. If I trace this guy down and this one down, it's intercepting the same intercepted arc. It's like, what? It's the same guy. Okay, now if this happens and you get two inscribed angles that eat the same thing, then the only thing that could be said about these two angles is they have to be exactly the same. And 2x plus 13 would equal 3x. And you'd set the two equal. Now, that only takes place if the two are eating the same intercepted arc. Now, if I subtract that, I get x, and I get x is equal to 13, and I'm off to the races. Again, tracing down those lines is the key to seeing what you're dealing with. You're like, oh, that one's going down to B. Oh, this one's going down to A, so that one eats this arc right here. Does the other one eat the same arc? You're like, okay, I'm tracing down this one. I'm tracing down this one. Cha-ching, it does eat the same arc. So if they're eating the same arc, they must be equal to each other, or 4x is equal to 6x minus 20. A little subtraction, I get negative 2x is equal to negative 20, and x is equal to 10. All right? Pretty straightforward concept about them eating the same arc. That's the key information right there, and they would be equal to each other. Now, some other interesting things that you can do with inscribed angles is you can inscribe some shapes. Now, what we're going to do right here is we're going to do day number 5 backed right on top of day number 4. It's kind of like the two of them go together. So you're going to watch both videos, and you're going to give both of these homeworks a try. Now, what if I actually inscribed, meaning put inside of a circle, inscribed it, a right triangle inside? Now, what happens here is if you inscribe a right triangle and you end up putting this right triangle, right angle right here in the corner, that right angle in that corner is an inscribed angle, and ultimately it would be, since this is 90 degrees, the arc that it actually eats had have to be twice the size, or 180 degrees. And if it's 180 degrees, then this line going right straight through here, must be a diameter. And it ends up turning out that way. Every time you put a right triangle inside there, the hypotenuse side turns out to be the diameter of the circle, which is really kind of cool. Now, number 9 says find x. Now, they should have put that this was a right angle inside here, or they told you that it was going through the diameter. If they give you either one of those two pieces of information, you know it's a right triangle. And ultimately, I think that's all they gave you, was that it was a diameter, putting this guy right here. Well, that would make this 180. And if this is 180 degrees, that makes that 90. And then a triangle still has to add up to 180 degrees. So you'd be like, 3x plus 6x plus 90 would equal 180. And that's because the triangle has to add up that way. Now, if I subtract, I'd get 9x is equal to 90, or x is equal to 10. Pretty straightforward, okay? Again, the key is that it's eating 180 degrees, which forces it to be a right angle. Same kind of question in number 10. Okay, it's a great time to pause the video and check to see if you can do that question in number 10 itself. And voila, amazing magical math appeared. And what I did there again was added up all the angles, set them equal to 180 because of the sum of a triangle, and then just did some algebra to come up with the x value for this deal. Now, I shouldn't have stopped right here and said x is 21. I think they're looking for angle B, so you'd have to plug that number back inside there and come up with an answer. 3 times 21 plus 6, and that'd be 63 plus 6 would be 69 would be the angle size. Okay? Now, number 11. Find the value of AB if AB is a right triangle. Now, they're trying to find out how long should this segment actually be right here. And I probably covered it up and shouldn't have done that. But that's going through the diameter is going through the center, so that'd make this a right angle. And don't forget, any times that you see this big old fat right angle right here, not only is it about triangle sums, but sure as heck, you can still use any right triangle information that you know from a previous unit, and that would be Pythagorean Theorem. And you could easily use Pythagorean Theorem to find that length as well, too. 16 squared plus 12 squared is equal to c squared, or 256 plus 144 is equal to c squared. And I think that adds to 400. And the square root of 400 happens to be 20. And cha-ching, bada bing. Who'd have thought circles and right triangles would be related? Yeah, that's why we learn triangles, right triangles, before we do circles. Now, other things that you could put inside of a circle may not be just a triangle, but you could put in a quadrilateral. You're like, what? You want to put a four-sided shape inside of a circle? It actually turns out to be a pretty cool activity of what's going on here. And it says a cyclic quadrilateral has all of its vertices on the circumference of the circle. So what they're basically saying, to be inscribed perfectly, is that all the vertices have to be touching the corners of the circle. Okay? Now, if that turns out to be the case, something really cool does happen here. And I'm going to erase these two on this side, and I'm just going to trace along here, and I'm going to be like, hey, this angle D opens up, and if I trace it along the idea right here, it opens up and it eats this arc going from this side to this side. Okay? Now, that's the blue one. Now, his partner on the other side, hey, angle B, you're going to be like, oh, hey, he's like, hey, I go over here and I touch this one, and I go over here and I touch this one, and I eat this part of the circle going around the other way. I eat the other part of the circle. So here's my question. Between the two of them, they eat the whole entire circle, but they're not equivalent to 360 degrees. They're only equivalent to half of the arcs they eat. Now, if they eat up together and they add up to 360 degrees, they eat the whole thing, but they have, at best, can only be equivalent to half. That means that the two angles that are on opposing sides, the non-consecutive ones, actually have to add up to 180 degrees. Sorry, that's not B. That should be D. So B and D would add up to 180, and so would A and C would add up to 180 degrees, just depending on which way you want to see it. Now, that concept is pretty easy to pull together right here. So you'd be like, hey, find X and find Y. Well, if I wanted to find X, I'd realize that this angle, X, and his partner across from him, the 80, those two angles have to add up and equal 180 degrees because they eat the whole circle, but they're only half of its value. So in this case, X has got to be 100. Pretty straightforward. Same thing would go with the other diagonal ones. These two diagonal ones in an inscribed quadrilateral would have to add up to 180 as well. So y plus 71 is equal to 180, and if I subtract that guy, y would equal 109 degrees. There you go. And now you found all those individual values. Now, that one was really done easily because it's got just numbers. But in 13, it's got some equivalences based on algebra. Well, again, the same rule applies. These two opposing corners still have to add to 180 degrees. They're not equal to each other. I almost did it. Wow. They have to add to 180 degrees. Okay. Combine your like terms. 7x plus 12 is equal to 180. Subtract your 12. 7x is equal to 168. Ooh, check my math there, guys. And I'm going to run home to mama here and try and figure out how to do this question. 168, not 58, 68 divided by 7. Cross my fingers. Woo! X is 24. And that, thank you, Matilda, for giving us the answer. All right, now I'm going to move down here to the very last one. Little review here. Again, remembering, find the value of C on this one. Remember that the guy across has got to be supplementary with it. That's got to be 130 degrees. There's just no way around it. Okay? And here's your review. Try a couple of multiple choice questions that might look just like this on the final, guys. Yeah, finals are really starting to be something to think about. They're right around the corner and only a month away. So start thinking about this. I'm going to pause the video at this point in time. Let's see if you can get the answer A through D or A through D on the next one. So pretty straightforward question. First thing I did was I added the two angles together and got 256. Took that answer away from 360 degrees, got 104, and realized that there's no way that guy's going to be 104. He's got to be half the size of it, and 52 makes the only one that makes any sense. Again, I'm going to pause on this next one. You try the second one. Second one. And see if you can come up with X and Y. Now, the second question here delves into an arena that's called a system of equations. And in my opinion, I would say the system of equations is probably a waste of time when you were doing it on finals. I would probably do this question with a little bit of guess and check. So I'm going to try this with you so that we can see what's going on. I think the easiest one to plug in would be possibly the bottom one. And what you really want to do is make sure that they end up making the diagonals add to 180. So if I plugged in 0 for X, this one would be a 98 degree angle. And if I plugged in 7 for that one, you would end up getting 12 times 7 minus 2. 12 times 7 is 84, minus 2 is 82. And it looks to me like those two angles would be supplementary to each other. So maybe I'm onto something. Let's see if it works on the other guy. This one would be 62. And if I plugged in 7 on that question, I'd get negative 1 plus 17 times 7. And maybe I'll get lucky on the first try here. 17 times 7. Ooh, I don't know that one off the top of my head. 17 times 7 happens to be 119. And if I subtracted 1 from it, it'd be 118. And 118 and 62. Cha-ching, bada bing. Got it on the first try. Woo! I live in Nevada and I gambled. All right. Good job, guys. And hopefully that makes sense how I just kind of picked and chose to make sure that they added to 180. All right. Good luck on this stuff. Big key things to remember in terms of what's to review here. If you inscribe a quadrilateral, the opposing corners will add to 180. If you inscribe a right triangle, then that means that it's going to be a diameter and a right angle that's inside there. Those triangles add to 180. If you have two inscribed angles that eat the same arc, then that makes them the same exact size. And then last but not least, the big kind of idea here is that the intercepted arc and the inscribed angle, you take half of it and you end up with the size of the inscribed angle. All right, good luck. Get her done.